From ancient battlefield strategies to modern digital transactions, the need for secure communication has been a constant throughout history. Sharing information secretly is crucial, but it's a challenge. Eavesdroppers lurk everywhere, eager to intercept our private conversations and steal sensitive data. Imagine sending a message to your allies while your enemies watch. How do you make sure only your allies can read it? This is where the art of cryptography comes in. Cryptography is like creating a secret language that only you and the intended recipient understand. It involves scrambling your message into an unreadable format, making it gibberish to anyone without the key to unlock it. This key is a secret piece of information that allows the recipient to unscramble the message and read it. For centuries, we've relied on mathematical algorithms for cryptography. These algorithms create complex puzzles that are difficult for computers to solve quickly, protecting our online transactions and communications. However, as computers become more powerful, the security of these methods is increasingly at risk. This is where the strange and wonderful world of quantum physics offers a potential solution: quantum key distribution. Quantum key distribution, or QKD, offers a revolutionary approach to secure communication. Unlike traditional cryptography, which relies on mathematical complexity, QKD harnesses the principles of quantum mechanics to create unbreakable keys. It's like having a lock that's physically impossible to pick. But how does it work? The answer lies in the fascinating world of photons, the tiny particles that make up light. Imagine sending a message encoded in the properties of individual photons. Each photon carries a single bit of information, like a tiny messenger carrying a secret code. What makes QKD special is that any attempt to intercept these photons disturbs their delicate quantum states. This means that any eavesdropper trying to steal the key would immediately be detected, as their presence would alter the photons. This ensures that the key remains secure, allowing for completely private communication.